everyone. Good morning. Welcome to ISRI's convention and today's session on REMADE Innovating Recycling Technology. My name is David Wagger. I'm Chief Scientist and Director of Environmental Management at ISRI, and I'll be your moderator today for today's panel. Before we get started on our session, there are a few housekeeping items I'd like to go over for your benefit. You'll notice badge scanners at the back of the room. Scanning in is not required, but doing so will help ISRI keep count of attendees, and in return, it will give you access to presentations and additional information after the convention. Also, please make sure your cell phone is turned off or turned to silent. That said, we do encourage you to use social media platforms, either using hashtag ISRI2018 or by following us on Twitter at ISRI. Please make note now of the emergency exits from this room. Emergency exits throughout the convention center are clearly marked with illuminated signs that are supported by the emergency power system and continue to function even during periods of power outages. In case of an emergency, guests will be directed to exit via the foyer areas to the convention center parking lots. If you have left something behind or have located an item that needs to be turned in to Lost and Found, please go visit our registration area. ISRI would love your feedback on this session. Please complete the session evaluation through ISRI Connect, ISRI's official mobile app. Select the session under Schedule, and then under Resources, you'll see the evaluation. If you have not downloaded ISRI Connect, you can do so through Google Play or the App Store. The password for the event is thanks AMCS in one word, where thanks is just capitalized and AMCS is in all caps. So the first of our panelists is Dr. Eric Peterson. He is Deputy Director at Idaho National Laboratory for the Center for Advanced Energy Studies. And until recently, he was the lead in efficient use and recycling at the Critical Materials Institute. Currently, he leads the Recycling and Recovery Node area for the REMADE Institute, a member of the National Network of Manufacturing Institutes sponsored by the Department of Energy and led by New York's Rochester Institute of Technology. He has spent the past 27 years performing research on polymeric and related materials focused on separation science and technology, from the most fundamental understanding of molecular interactions to construction and proving of pilot facilities using the materials that he has been active in developing. After a short stint at the National Science Foundation, he's been active in developing energy efficiency and renewable energy-focused programs. He holds a PhD in chemistry from Montana State University and a BS in chemistry and a BA in biology from Concordia College. Our second panelist is Philippe Blot, who is co-founder and head of customer development for EDX Magnetics, LLC. He graduated from the National Superior School of Geology in Nancy, France in 1988. Since early 1989, he has lived in the US, mainly in Salt Lake City, Utah, and has worked in mining, mineral processing, and metals, developing and applying a variety of computer modeling techniques to analyze, optimize, and design processes and flow sheets in iron and steel, base and precious metals, and industrial minerals and fertilizers. His involvement with the scrap metal recycling industry started at the beginning of the EDX project at the end of 2013, with the techno-economic analysis and the technology to market parts of the ARPA-E-funded project. Philippe will describe how the project has evolved from an initial idea to a quarter-ton-per-hour prototype, which has been tested on real material, fine Zorba, and produced significant value add for the processor, and how the next phase is organized to produce an industry-ready 3/4 to 1 ton per hour machine. Before we get to the panelists, I'd like to give a brief history of ISRI's foundational role in REMADE. If you're not familiar with ISRI, we're the US-based recycling trade association for private sector, for-profit recycling companies. We have about 1,300 members with 4,000 facilities in 34 countries. ISRI has a wide range of priorities, but there's a direct intersection between ISRI's priorities and REMADE in design for recycling, scrap is not waste, and education training and networking. ISRI members also recycle a variety of commodities, and the intersection between those and REMADE cover ferrous and non-ferrous metals, paper, plastics, textiles, and electronics. The US recycling industry, based on 2016 data, is a $117 billion industry. The industry processed and recycled more than 130 million metric tons of material. About half of it is iron and steel. About 40% of it is paper-based commodities. You'll see in plastics, it's a very small amount that we've tracked, but the potential is much greater, and we think REMADE can help us grow these numbers and recycle and process more materials and displace more use of primary materials. This is a brief history of ISRI's role in REMADE. I am not going to go through all of it. You're welcome to look at the details while I give you some takeaways from this. First, ISRI has been involved with REMADE since 2013. Since before REMADE was REMADE, it was initially an idea coming from Eric Peterson and Idaho National Lab, known as the Institute for Recovery, Reuse, Recycling, and Remanufacturing, or R4I. You might hear a reference to R4, but R4 represents those 4 Rs. The second takeaway is, if you look at the first 3 dates, those represent meetings where experts in government, academia, and industry got together and thought through problems related to all of these activities in R4 space. We looked at target materials, processes, collection systems, everything from atom-based design of materials all the way to collection systems. The point is that REMADE is not an accident. A lot of effort and thought went into it over about the 3.5 years it took to go from idea to evolve into a national manufacturing institute. That happened officially in June 2016, where REMADE became REMADE. The Institute was launched officially in the beginning of 2017, and ISRI was proud to become a founding member in November of 2017. The potential benefits of REMADE are both directly impacting the recycling industry in ISRI as well as the rest of materials manufacturing. We have designed for recycling methods and technologies for increased recycling efficiencies and yields, reduced life cycle impact of materials. There's design for manufacturing, remanufacturing, which are closely tied to design for recycling. Economic competitiveness enhancement, high-paying U.S. jobs in the semi-skilled and skilled space, strengthened U.S. science and engineering vitality, and importantly, but not to forget, curricula for the next generation of technologists in the R4 space. We need to develop technology. You may have heard Carlos Gutierrez talking about the importance of technology. To improve recycling and sustainable materials, we really need to develop technology that'll give us a big lead globally and position us well to continue become a more sustainable society. Currently, ISRI is founding member. We also represent the recycling industry at REMADE. We also participate in the Strategic Advisory Committee and the Technical Advisory Committee. So with that introduction, I'd like to call Eric Peterson to make his presentation.
Thanks, David. So the REMADE Institute has been renamed, as you've heard, from R4I, and it became the Institute for Reducing Embodied Energy and Decreasing Emissions in Materials Manufacturing from the energy aspect of the Department of Energy. So that's why it became REMADE as opposed to R4I. And it's one of those things where we, as David said, we're a member of 14 of the national institutes for manufacturing, which vary all the way from things to work on recycling, recovery, reuse, like we are doing, to things like lightweighting of vehicles and making more efficient processes for doing separations and catalysis. And so there's a broad range of things they do, and there's certainly, it's an opportunity to work with a lot of different industries throughout our country and to bring back some of the manufacturing base to this country. The challenge that these institutes try and cover is that space between strong technical development at the basic science side and the application side, and helping to fill the valley of death for many technical opportunities by bridging the gap with these institutes, very much like the Germans have done with some of their institutes. So what we're doing is we're looking at using, obviously, government and universities typically do the basic science side and develop fundamental science, and the industry tends to want to do the applications and demonstration. And what we're trying to do using these institutes is to fill that opportunity, that space where no one really wants to fund a technology from that upward step inward, onward out toward the full demonstration and testing effort. REMADE is focused on early stage applied research and development. And the goal, of course, is to reduce the embodied energy that one finds in those systems, so we don't simply bury it. Once we've made the metal, once we've made the polymer, we want to save that energy and recover it. And we also want to save energy in terms of the carbon emissions. It enables utilization of secondary feedstocks and hopefully will help to increase utilization of those systems. We want to reduce the primary materials consumption by significant sums, and I'll summarize that in the next slide. And we want to promote the widespread application of new technologies across a wider bandwidth of industry. For example, some of the processes that the mining industry uses very well can be used in the recovery processes here in the recycling world. This is one of the institutes. It's a consortium of universities, national laboratories, and the private sector, so it's a public-private partnership with government underpinning funding to get it launched. We are focused on the early stage applied research. The collaborative consortium will facilitate leveraging the R&D side of things, as well as using the national effort with the industry to leverage what they've already done and hopefully make it a stronger opportunity. Additionally, you heard yesterday that we need to be training our workforce, and this is an opportunity. We have a very strong effort in helping to train workforce at universities as well as at the national laboratories. So there's a really golden opportunity to broaden your education base for your personnel. The goals we've set are pretty large and probably a little bit ambitious, but that's good for the government to do these things. We want to reduce the total primary feedstock consumption by 30% and increase the secondary feedstock utilization. We want to certainly improve the embodied energy recovery in 5 years. So we've got a 5-year time frame here to work with before we have to be independently sustained and funded. We have a 30% reduction in energy demand for secondary feedstocks, in other words, make the processes more efficient and build the technology to do that. We have a 20% increase in our 10x increase in our primary feedstock use, our reduction in feedstock use and enhancement of our secondary feedstock use. And then we want to make this go across industry, help it to become part of what goes across industry and is used by a variety of different customers. And finally, we want to make the cost parity, bring these secondary feedstocks into cost parity with primary feedstocks where we can. And therefore, it'll make it a much more effective process to use. Our mission is to enable early stage research and development, where the basic work is done by the labs and universities, and we facilitate industry funding into getting it beyond that valley of death. We have 4 feedstock waste streams are definitely defined for us to use, and those are metals, polymers, e-waste, and fibers. Fibers primarily being focused on paper. And it's an opportunity where we've taken this and divided it into 5 separate nodes. The systems analysis integration effort, those are folks that are focused on understanding the markets, how they interact, how the feedstocks come in, how we collect things, and bring us the data that we need to make those things work. We also have a design for reuse and disassembly component, and that component is focused on how do you design things, materials, systems with the industrial partners so that they can be disassembled more efficiently. We have a manufacturing materials optimization group that is focused in on understanding how to take the scrap that comes off of molding processes and so forth and reusing it efficiently, getting it back into the system, perhaps without having to go through a full recycle of it. We have the remanufacturing and reuse effort, and those folks are focused on reusing and recovering material and directly cleaning it and putting it right back into systems, understanding how to evaluate electronics that come out of perhaps a Caterpillar or something like that, where we need to be sure they work and work well. And finally, the recycling node, which I get to lead, which is understanding how we gather materials, how we identify those materials, how we sort them, how we separate them, and how we separate not only the tin cans and the beer cans and the Coke bottles but also how do we separate those at the molecular and atomic level. So we have roughly 15 or 16 orders of magnitude in size we get to work through. It's a tremendous challenge and opportunity both for all of us. And finally, we need to look at how do we do contaminant removal, reprocessing, and finally, what do you do about disposal? Because we can't reuse everything or recycle everything. We're looking at development of widespread technologies, I've indicated a couple of times, where we're looking at how do we get the information, how do we design the different tools for the remanufacturing and recycling opportunities, how do we get rapid sorting, and one example we're going to hear about for rapid sorting will come from Philippe Blow, who will be discussing that, what we're doing with the University of Utah. How do we do separation of mixed waste, and how do we clean things up? What processes and what new novel ways of cleaning things can we use? And finally, what's the reprocessing approaches that one can use? We used the DOE bandwidth studies plus an additional set of studies that came out of DOE to understand where the most energy was being lost in the embedded format. And we looked at we got three projects that are starting right now in the area of advanced solid-state eddy current sorting, which you'll hear about. Another one is a platform technology for polymer recovery and sorting coming out of Argonne National Laboratory. And finally, we're going to do an assessment on paper fiber and how do you get contaminants out of that. And so these are the three initial projects that are being funded and are starting at this time. A brief summary of each of them is provided here. Argonne National Laboratory leads the polymer recovery and recycle effort, in which we're definitely interested in very specific needs for separating computer case polymers and getting them for high-performance polymers that can be recycled and reused. The second one is being led in the paper area is the University of Miami, and they're very specifically focused on assessing the impact of single-stream recycling and understanding how we get contaminants out of paper fibers such as shards of glass, shards of plastic, and some of the oils and greases that come with food. And finally, at the University of Utah, we're looking at rapid sorting of scrap materials with solid-state devices, and that you'll hear more about shortly. There's a list of benefits provided here, and I think each one of these you can read on your own, but they're all focused on reduction of energy and recovery of embodied energy, and we certainly can provide you a slide deck so that you can read through the details here. How does this institute work? It works like all of the manufacturing institutes do. We have research, we look for innovation, we look for training and development of the specific employees and opportunities for people to learn. And also we have certain efforts in, obviously, technological breakthroughs, which then gives the overall project results. We start with the idea of a concept, which you can submit to the institute. Those are then selected and then we ask you to write a pre-proposal, a couple pages to us, to tell us what you think you want to do. And we take it, evaluate it, and look at what it offers us in terms of energy savings as well as technical balance within our portfolio. If we come back and ask you to write a full proposal, there are two levels. One is exploratory, a little less funding, but an opportunity to explore an idea. And then a full proposal offers an opportunity to really develop something a lot further. If we call you in for full, your chances are very, very high. They're probably better than almost anywhere else in the system. If we call for a full, your chances are pretty much 1 in 3 to 1 in 4 for winning. So it's a very good opportunity to get some funding. We ask you to obviously be a multi-dimensional team. We want to see academics as well as national labs and the industrial folks working closely together as a team to make this happen. And the first call closed on March 15th. It's a $6 million effort. We expect somewhere between 15 and 20 awards in that area, and we expect them to be out in September. We're right now in the middle of the evaluation of the proposals. We have another open call for another $6 million coming up probably about July 1st. The listed date of mid-June looks a little early right now, and we expect the awards to be out in November, December timeframe. Again, the same process. The team, I want to just introduce you to a few of the folks involved. Nabil Nasser at RIT is our CEO. And then Magdi Azar out of University of Illinois, formerly General Electric, is our Chief Operating Officer, our Chief Technology Officer, I'm sorry. And there's a few other folks here that really fill in the head office at the New York area. On the technical leadership team, we have the folks that are working in the systems area, Barbara Reck and Tom Gradle. In the area of remanufacturing, it's Mike Thurston and Mike Hazelcorn. Recycling, myself and Mike Free at the University of Utah and I'm at the Idaho National Laboratory. And then in the areas of design for reuse and disassembly is our Deborah Thurston and Bert Ross. And then Pradeep Rahandi and Alan Liu lead the area of manufacturing recovery. In addition to this, we have some test beds that have been designated across the country. For example, there's a test bed at Idaho that focuses on advanced separations of large-scale multi-component streams, which is an outgrowth of another program where we have large machines that will allow us to do compression, testing, evaluation, and detection of systems that are there. It's a grew out of a biomass effort. There's a lightweight testing test bed at University of Utah, and there's a variety of others cast around the country, so that we have ways of doing upscaling of processes that are developed at the universities. Our team is very, very large. We have approximately 65 members. This is not as current. They called me last night and said, well, we have a much more current map. I said, it's already submitted. We're going with it. You'll see ISRI located in the upper right there. It's very prominently shown. And we also have a variety of other companies, and you can see other national laboratories, universities, and industry are all part of this consortium. So with that, I'd like to say thank you for your time and invite you to visit our website and also chat with me at the end of the session. My card is on the back there. There's some collateral information about the Institute sitting on the table. So feel free to grab that and chat after we're done. Thank you.
Thank you, David. So now that we've gone through sort of the global strategy and vision of what the REMADE Institute is pushing and sponsoring, I'm going to present the project that's done at the University of Utah, and EDX Magnetics is the company that's the offshoot of that project that was just started last year. We followed a process through grants from the Department of Energy that started in the beginning of 2014, and the funding agency was ARPA-E at the time. That grant ended at the end of 2017, and we're now starting on a grant funded through the REMADE Institute, which is a reorganization of those programs that were inside the ARPA-E, right? So that was the ARPA-E Metals program, and they had the same goals as REMADE is doing from the technical standpoint, with a focus on light metals, because light metals are energy intensive in terms of primary production. So the idea was to try to recycle as much and sort those light metals to keep that embedded energy within the country. And as far as the method to achieve that, they recognized that we needed new sorting technologies and to develop new ideas and try a variety of new ideas to see what was possible from the physics standpoint. And it also had a component that was the market side. So the technology to market and techno-economic analysis are the components that says this technology is great, but is there a market for it? And can we build it for a price that the industry can afford? So is there a value to this technology? Because we can develop things that are extremely beautiful and great, but if nobody can afford it, there's no point of doing it, right? So from the start, there was a research component, and there was also an application component to it. The idea came from the principal investigator at the University of Utah, Professor Rajamani, and he said, well, instead of doing separation with eddy current machines right now, we generate the eddy currents by generating an alternative magnetic field by rotating a drum that's populated by north and south stationary magnets. Instead of generating the magnetic field that way, why don't we generate it through directly an alternating current? So the idea is we build a magnet that looks like a toroid of some sort of material, and we put the material in the gap that we cut in the toroid, generate the field through a winding around it, and depending on the material, that material will kick more or less as a function of its density and its conductivity. That's the sort of theory that we started with at the beginning. And I say sort of theory because the formulas that had been derived in the literature were not quite right. The general principle was there, but the details of the formulas weren't quite right. In any case, we started with a very simple setup that we put on a little bench scale that was built the first year, and the idea was we need to do the proof of concept. So at the end of the first year, the RPI came with what they call a challenge, where they gave us a bunch of aluminum alloy coupons of a certain dimension, very strict dimension, and they said, well, can you sort those? And of course, nothing was marked, and that's what we ended up with. And we did some experiments, of course, as we knew the test, and we took different coupons from different alloys, and we say, well, that should be about what they're going to give us. we don't know, and we design the magnet and the frequency, and the little red apparatus that you see is just a feeding mechanism for one coupon at a time. And we got there 200-some coupons, and we did a couple days of testing, one by one, like this, at 3 different frequencies on that magnet, and we managed to actually get a result that wasn't random. We sorted, that was the result of our sort, so we started with 244 coupons of different aluminum alloys, and we ended up with 4 categories that corresponded to different conductivities and densities. I mean, the densities was always the same because it's aluminum alloys, but they had slightly different conductivities, and we were able to sort those. So they said, well, you actually performed quite well for this test, so you're getting 2 more years of funding. Now we said, well, 2 more years of funding, but this is still a proof of concept, and the formulas don't quite work, so we need to do science. And that's when Dr. James Nagel came in on the team, and he has a doctorate in electrical engineering with a specialty in numerical modeling. So he started developing numerical models to calculate the generation of eddy currents in the field that we have and the force that's generated on these currents from first principle physics. The materials we were looking at sorting at the time were a mix of copper, aluminum, zinc, and brass. And here we see their conductivities in megasiemens per meters and their densities in kilograms per cubic meters. The function, the force, is a function of the ratio of conductivity divided by density. But it's not a linear function. And we also derived that function mathematically, but you see that the distribution of the currents in the particle on the 3D plot on the left is not a point. So there's an analytical function that you can derive, and that was actually published in a paper that we did. And there's also a numerical solution to the problem depending on the shape and the size of the particles. Once we had those elements, we built a little test bed with a magnet at a 20-degree or 30-degree angle and a vibrating feeder feeding a little conveyor belt that projects the material through the gap in the magnet, and depending on its conductivity to density ratio, the material kicks more or less. You see that in this case, we have a simple separation between our aluminum materials, and that's all aluminum alloys in this case, and the copper, brass, zinc that are the drops on the other side. And then we said, well, that works reasonably well for zebra type materials. So something that's in the 1 to 6 millimeter kind of range. And we can make a good sort there. So what happens for a larger type material like a fine Zorba, up to 1 inch? We did this testing and we had mixed results. It was possible to do a decent source until probably about 3/4 inch with this setup, except that the gap has to be larger for larger particles, and the physics don't work over a certain dimension. So we said, well, we need to refocus on this, and now we have something that works for zebra. Let's go test it and make something that's the next prototype thing. And that's what we tested in a facility in Utah that produces about 80 pounds an hour of zebra type material. That was the setup we had, and we were able to produce out of their zebra material a number 2 copper product. And for them, it's a big benefit because they can sell that at a good price to the Kennecott smelter that's almost next door. And then it goes back into making pure 99.999 copper. And we presented an evolution of that prototype at the ISRI meeting last year in New Orleans. and it was a running prototype on material from that facility in northern Utah. And we had good interest, and we had also developed a way now to control 3 magnets in parallel to achieve larger tonnage. However, we still had challenges in terms of how you run this machine in an industrial facility, because you drop particles inside a gap in a cut toroid, and if you have magnetic materials that comes in, it gets jammed in it, your magnet's gone in seconds. Or you have the practical aspect that you have to feed a line of particles through that gap, which limits your tonnage severely. So we said, well, we need to design something that is much more industry standard in terms of its look, and also safer to operate and not so difficult to operate. So we need to go from this gapped magnet design into something that's going to be embedded inside a conveyor. And that's the current implementation of the system. So now we put material on the belt, and the stationary magnet that is powered, the electromagnets, are lined up just under the thin conveyor. The magnetic field is projected over the conveyor, and the particles that are light and highly conductive kick higher, and the particles that are higher density and lower conductivity just drop. So we have a very clean separation between heavies and lights. From the modeling standpoint, we use the numerical modeling to design the magnet, and we went through several iterations there. And from the manufacturing standpoint of the magnet, now we build it in a modular fashion. So we have whatever width of conveyor we can make, which solves our tonnage issue and our capacity issue. Now we combine that model with a kinematic model of the particles coming onto the conveyor and the force kicking them on the vertical axis, and we develop a trajectory which gives us where to put our divider. We're going to go right in the middle there on the divider. So once we have that, we built it. We started building something that was narrow a channel on the conveyor, and we used calibrated cylinders of aluminum and copper, and we got a perfect split. So we said, well, now let's try to use the same idea as we had on the fine zebra and do 2 lanes of that material. And on the right, you see an image of the silvery gray particles on the aluminum side, and you see that they kick higher than the copper that's in the middle that just will drop with higher density. Through several evolutions after that, we ended up with the current machine that we have and that we tested with, that is on the picture on the lower left. So at the top part, we have a conveyor that is there a pointer here? There you go, okay, yep. So let me try to not shoot it in, oh, wrong. Right, so here we have a conveyor that's a rectangle with 4 rollers. In this part here, we have the magnet. We feed it through the hopper here with a vibrating feeder that distributes the material on that conveyor. That conveyor goes at about 2 meters per second, and the particles are kicked up, and then there's a divider here, and we go into the 2 different buckets there. The electronics to control the magnet are in that cabinet down here. So this is the current setup we have, and the material we used is in this pie chart here. So we have, we start with 48% of cast aluminum, 22% of wrought, 4% copper, 14% brass and bronze, and 12% zinc and other. That's the fine Zorba that that customer in northern Utah produces for 8 hours a day at about 3/4 tons an hour rate. So this is minus 3/4, nominal minus 3/4 material. And we produced, we got 2 or 3 big boxes of that material. That was like 3 tons of it. And we ran this 5-gallon bucket at a time, and we took samples, and these are the 3 results that we got. And on the drops, the heavies, we have 14% copper, 30% brass, 41% zinc, and 12%, 14% aluminum. And on the throws and the lights, we have 96% aluminum between the wrought and the cast, with a little bit of copper and a little bit of zinc. What this tells us is we use these results, these sample results after that, to mass balance the system. And I got 32% by weight goes in the drop, 68% goes here, and we have over 90, often over 95 recovery of the cast. We have about 90 on the wrought, and we have 93, 94% recovery of the copper, the brass, and the zinc into the drops. So in terms of process efficiency, the recovery being how much of, let's say, the copper goes in here. Well, 94% of the copper that we start with goes into the drops, and only 6% goes here. And in mining and processing in general, when we have a separation process that is 90+% efficient, it's pretty good. So the customer actually just went pick up his material 2 days ago, and he says, well, when can we have one on site? Because right now I have pounds and pounds and pounds and thousands of pounds of this stuff that I can't process, that doesn't go anywhere. So that's the next iteration of this is right now what we're doing with the REMADE Institute grant is build a 1 ton an hour machine on those principles. The continuation of the program now is, now that we have engineered a system that is under a belt, we're going to move the Zebra side onto the same type of system. And for the Zorba, we're widening the lane to and industrializing the electronics to get to an industrial machine. So in conclusions, what we are trying to do here is demonstrate how we develop new processes using technology with a little bit of luck. It always helps. And going from the basic physics to how we design the magnets, to then test and operate and run Monte Carlo simulations to see where the trajectories of all the particles are going to go, position it and design the machine, and operate it with software as well. So this is what we envision the machine will look like. It's probably about 8 or 10 feet long, 4 or 5 feet high, and 3 feet wide. And that should be in the 1 ton an hour range for fine Zorba. All right. Well, thank you. And I'd like to, I guess, open the floor to questions and discussions. And we'll go Control F5. Oops, escape first.
Okay, we have about half an hour for questions for our two panelists or myself. Do I have any questions? I'll take moderator's prerogative to ask the first question. I saw a hand go up there, and please use the microphone so we can get it recorded.
I have two questions for Eric, I believe. I might have missed it in your presentation, but I'm Karen Pollard. I'm with the EPA, and I deal with electronics. One of the things that has happened in electronics industry is they have gone from a very simple concept of few materials, maybe 12. Now, just one of the smartphones might have 90 different materials in it. And I didn't see in your description of the different parts of REMADE where understanding the different materials in the electronics product or any other product, I think probably though with what you're looking at, electronics is the one that really fits this question. Where you're looking at those materials that are not currently being recovered for whatever reason and determining whether or not they should be recovered because understanding what's in these, you've got the rare earths, you've got lithium, you've got graphite, you've got all these things that are actually fairly expensive when you buy it in a raw material. And yet no one's really kind of looking at how we can start recovering that. I do realize that you have another, goes into my second question. You do have another institute, the Critical Materials Institute, which does deal with some of that. And so my second question is, how do you work with that other institute so that you're not doing double duty?
First of all, tell me I've got to turn this thing on. I'll figure that out.
You can come down and work this one.
There we go. Yeah, let's see.
This one works really good.
Now, just come down. There, oh, there you got it working. I'll just hold it. I don't have to lean into it then. So, Karen, thank you for that question. It's a sensitive question, obviously, within our governmental circles that we don't overlap and don't duplicate. As my introduction suggested, I did start out with the CMI, the Critical Materials Institute, and started the recycling effort there. Then this grew out of that. We are being very careful not to overlap. In CMI, they're focused on the rare earth elements specifically, and we are then picking up the balance of the materials that come out of these things. And if you look at our structure in the 5 nodes for REMADE, there is the data gathering and information group at Yale. They're helping us to understand what's there, where they fit, what percentages, what the costs are, and what the values are. And so they're really helping us understand a lot of the detail. Then we start talking to people, various groups about the, let's say, metallurgy and so forth, and what can and can't be recovered, what is today recovered, and then how do we work from there. into getting those things which get slagged off to the side. So, for example, I've worked a bit with a major copper producer, and that copper producer has rare earth elements coming through from their ores. How do we get those? Well, what they do is they slag it. Now, what is the structure of those slags? How do we get the materials out of those, and how do we extract them efficiently? Or can we? And the question becomes, can you do it, and is it worth it? Because they have arsenic, tellurium, and a few other things tied into those slags as well. So those are the kind of questions we're asking, both from the economic side and from the practical chemistry side. And we work with a couple other folks. We've talked with other folks they're actually in this room that commercially recover metals, and they have also indicated their slags are tough to get at. We're looking at samples of slags. We're asking for samples of materials that are where these things are, and we're working with them to develop approaches to getting at those things. So it's a question of cost, basically, and if it's appropriate, we'll chase it. It has to be proposed into the Institute. We'll put it into our annual planning, and then it has to be proposed in and supported by the industrial partners. You know, these are not grants. These are contracts. And so it's a little different way of approaching what you're going to do. And with the industry cost share, you're very, very much directed as to what really can be done and will be done. They're not academic studies. We don't just send a professor off to figure out what's there. So it's a whole different mentality when you start working with these. These are not grants, as I say. They're very specifically focused efforts that will go there. Does that help? We're also working with another group at EPA, as you well know, in some of the recovery and sorting efforts on the ORD side. So.
Follow-up question to Eric on the project with the Argonne Labs. There has been an industry initiative that I've worked on with closed-loop recycling of plastics coming out of e-waste. There are two issues that I'd like to ask your opinion, direction, impression that have surfaced during those efforts and how they relate to REMADE. One is the issue of brominated flame retardants and the way to get those out of products that can be reintegrated and reused that are in compliance with the ROS standards for eliminating brominated flame retardants is one issue. And the other has to do with the geography of the supply chain. In terms of implementation on a practical level, the pellets that get reintroduced go through a supply chain that is in China and will be in China. And there's been some short-term disruption there, but the general question, not only with plastics, but with other materials as well, including some of the metals that REMADE may get into, is what's the approach with respect to domestic recovery of resources and commodities and recognition of the existing global supply chain? Thanks.
So let me summarize. You actually had three questions there, I think. I'm trying to be sure I get the right ones. One is understanding domestic supply chains. The second one would be talking about the geography of supply chains in the country for the recovery side of it. And then what are people thinking about the brominated polymers? Fair? Yes. Close enough, okay. Let me start with the domestic long-term supply chain, large supply chains, and that's where the Yale group works with us. And then there's also another group at the INL that specifically focus on understanding supply chains, building models that we can use to understand where they're going, where product moves, how it moves, and where is it most efficient to begin to think about processing. Today, we have a lot of small producers, everyone calls them mom and pop shops, that collect material, do a little bit of processing, separating, kind of categorizing it. Then it goes on further to other processors, and finally gets to the majors. Either get shipped to Europe or get shipped to China or shipped to other countries for processing. And here in the States, it's hard. How do you collect something? And well, on the West Coast and East Coast, it's easy relatively because there's high population density and people are there, and you get much larger quantities in those areas. If you have somebody out in the middle of Montana or Idaho or Iowa, it's hard, or Utah, it's hard to collect these materials effectively and transport them. We heard yesterday about the transportation issues involved in moving these materials around. And these models are being used as a way of understanding how we get material from one place to another, and where do you want to process most efficiently? Is it best to collect the stuff in a small town and take it to the next town over and process it there? Or should you process it in a small town where it's collected? Those are the kind of questions that are being asked, and the models that are developed here are based very much on what we're doing in our agricultural industry for switchgrass and things like for the biomass efforts. We've developed a couple of initial node approaches where the material goes to a pre-processing node and then is shipped to somebody like a major processor for the final processing. It's a pretty exciting way of looking at it, and they balance that with the cost of the material, the cost of transportation, and they put in what the markets are doing. Is it worth holding it somewhere until the market rises so it can be transported again? Or do you want, transportation is killing you in a lot of this, so we have to figure that out and understanding where it goes and what's going to happen with it. So that's one of them. The brominated issue is a big one. That's been worked on at universities around the world, quite honestly. I've visited plants several places now, and all of them are having the same questions. Can we get it? We can get most of the bromine out, but when is enough? And how much will we allow, in other words? And yeah, I've got one proposal pending right now that is talking about brominated polymers. And I expect in the next round to have 2 or 3 of them come in to take a look at understanding when is enough and what's appropriate. Yes, right now we're not touching the halogenated polymers, we're touching only the computer cases. Very much like what some of the stuff Dell has suggested they want to see. And we're helping them to modify some of their processes potentially to be more efficient and make their separation more clean. That we've done it. The folks at Argonne have done work with the automotive industry already, and they're able to pull out some of the alloy polymers that are used in dashboards and under the hood components, and go back through the pelletization process and reintroduce them as a secondary feedstock. So we have a basis we're running from previously funded effort at the Department of Energy, and we're taking that and expanding it into the computer e-cycling business, excluding brominated, halogenated polymers right now. Yeah.
Are there other questions? Well, I'm going to take a prerogative of the moderator. So Eric, from your perspective as sort of the programmatic perspective, and Philippe, from your perspective as an implementer of a project, what do you see as the role of ISRI member recyclers and equipment providers in REMADE? I remember that 4 years ago here, we had some researchers from a university come and talk about modeling separation systems downstream of a shredder, and the comment from our members was, well, we've already figured all that out, it's not new. So maybe there's something you would comment on about sort of the level of effort and the role that members can play in truthing some of the ideas. I mean, you mentioned, Eric, taking agricultural as sort of as a proxy for this, but it may not be the same as what our members do every day. So how important is that, and sort of what do they get out of participating in REMADE, that kind of thing? And Philippe, from cooperating with them, you have some perspective on that as well.
Well, from our standpoint, being a test bed, that potentially gives us access to material that people don't process right now or ship as bulk mixed products, and see what we can do with it. So that gives us a variety of samples, because this market, everybody produces something a little bit different. There's no real standard. What we are trying to do with our magnet is design a process for a specific sort, and that's also flexible. And if we can do that and test it on a variety of material, that gives us a much bigger sort of testing sample to go with. Right now, we've used a few customers' products. That gives us access to potentially, 1,000 customers instead of a handful.
So from a broader perspective, I would dare to suggest that the role of ISRI members in REMADE is to help you help us help you, if that makes any sense at all, in a kind of a roundabout way, to help us grow what is understood, what is known. The assertion of you've already done it all, you probably have done a lot of it, but is it complete? Is it as fully efficient as it can be? Probably not. Can we help to grow that opportunity with you, leveraging government resources to get you the next step to make your processing efforts more efficient, more precise, and giving us opportunity. Participating in this offers you, with open sharing of ideas, obviously gives us an opportunity to do these things with you. There's certainly the opportunity to upgrade your product so you get greater value out of it, hopefully at a modest cost to upgrade. And then there's also the reduction in losses of these materials to landfill, and also holding the embedded energy of these materials out of landfills and holding them in this country so we can process and actually reuse these materials as much as possible in the USA. That's it for now.
Other questions?
Hi, I have a question about the embedded energy discussion in the projects. So when you're looking at these projects and you see that there has to be sort of an economic benefit that's going to come, that it has to be economically viable to let's say extract rare earths that might be in slag, for example. But at a certain point, it's how much energy needs to be spent into there. And so, is there a metric that you're creating to kind of develop an understanding of the environmental effect and a cost to that, and how that would make like that balancing effect? Because you have some businesses that may seem as it is better to containerize it or separate it, segregate it, and keep it off to the side for its environmental effect. But then it may be better to more economic to pull that and try to get those rare earths out. What's the sort of thinking philosophy behind how you determine what those costs are, the environmental cost or benefit versus the economic cost and benefit?
That is one of the biggest challenges we meet every day in terms of a life cycle analysis. For every project that goes on, we have to have a life cycle analysis and a techno-economic analysis before it can move forward. And they're pretty soft. They're pretty simple because these are concepts that people are presenting, and they're not necessarily fully fleshed out. But we try to get an idea of based on the TEA or LCA, that these things make sense. The metric will come in the form of carbon dioxide equivalent and or energy investment, so to speak, in the material, and how much do you get back. So obviously and finally, the real thing we ask for people to do is come back with a bit of information about how much is it going to be, how much is the product worth at current prices going back into the market. So can it be cost competitive with virgin material? That's really one of the bottom line questions we ask every time. Can we get cost competitive? If it isn't cost competitive, it probably is not worth doing. The example of what we saw today with what the EDX approach is that if you upgrade the Zorpa to a certain point, it's worth a lot more to the producer, and therefore they can make a better profit off of it, and the payback time is very, very much reduced on that piece of hardware, so it's worth it. So the metrics are pretty simple.
For us, the metrics are the market metrics. So you guys are not going to buy a piece of equipment that's not going to pay itself back in 1 year or 2 years. Depending on the company, you have different metrics. But our sort of rule of thumb from talking to a variety of people in the industry is the unit has to pay for itself in a year. That's it. So you get pricing of the two products versus pricing of the feed. And if the difference is $500,000 over a year, that's pretty much the price that you need to be under.
So, a couple other questions. Another part of my job is dealing with manufacturers' standards for greening up the electronics. A lot of questions come to me on what they want to do. Some of the questions come with regard to putting carbon fiber into the plastics, makes them nice and strong. However, what is not answered is is that going to be a problem for the recyclers at the end of the day? When these materials need to be recycled, is that going to be a problem? Is it going to contaminate the rest of their plastics stream? That same question is with the bio plastics. We know the answer on that. It does contaminate the rest of the speed. They melt at a different rate. And so we said, you have to figure out how to tell the recycler that this is something different. But are those types of questions are things that I see that sitting where I'm sitting, where I'm talking to the manufacturers about what they should or should not be doing with their electronics. Those, to me, those are ways that you could be, the REMADE could be very helpful in kind of predicting or giving advice on what is going to be a problem at the end of life, because the manufacturers don't know. They're looking at a very sleek, wonderful product that is going to hold up when you drop it. And I don't blame them. That's exactly what they should be looking at. But somehow there needs to be somebody who's looking at the end of life as well. So if somebody can talk to how REMADE might be able to do it, or maybe how the practical, my problem is that the recycler themselves don't know these questions are being asked, so.
I'll go first. I have some thoughts, but I'll let you go first.
I'll take a shot. The shot is, this is a pretty generic shot right now, but you're asking, this is a two-headed question, right? There's the regulatory side of it, right? And there's also, you come from a regulatory body, so let's just say that there's a question there.
These are voluntary consensus standards.
That's
They are
fine.
not regulatory standards. So that's the part I work on.
Okay. I stand corrected then, but the question comes, yes, there needs to be some way we can tell the recyclers on these materials what can be done. Now, for the carbon fiber composite specifically, there is a whole other institute named ISRI that's focused on recycling, has a chunk of it focused on recycling of carbon fiber composite materials, and they are the ones who will handle the carbon fiber composites. Because we don't want to overlap, we will probably let those go there. But in general, with these polymer alloys and blends and so forth, there's a very complex approach to what one can try to do there. And it's a challenge because everyone wants to keep their alloy kind of proprietary. They don't want you to talk about it. But there are some general principles that we are using in how we go about taking these polymers and helping recyclers to understand how to handle them, and general processes that we have proposed to develop using technology coming from UMass Lowell and or other major polymer institutes to help us grow these things. We're working with one of the contractors who works very closely with you, RRS. They're a member of REMADE, and they have a very broad background here in terms of how to start looking at these recycling processes in general and how to help recyclers get that next step. So there's a bunch of different things going on here, from the most basic science side to an applied effort, and understanding what can be blended and what cannot be blended and can still be successfully either injection molded or blown molded or what have you. So we're looking for ways to not downgrade We're looking for ways to at least cross-grade on these systems. So, yeah, there's a lot of stuff being done here, but a lot of it comes out of our economic studies, again, with our group at Yale, understanding how to do that, and our remanufacturing group in the remanufacturing node. So there's different ways we're doing it.
I don't think I have anything to add to that. It was quite complete. We have about time for one more question, one more burning question. Okay, well, let's thank our panelists, Eric Peterson and Philippe Blow. And I think they might have a minute or two afterwards to take questions from you up here. But thank you for attending today's session on REMADE, and we hope you enjoy the rest of the convention. Have a great day.